A silent stone drifts through the inner solar system, older than Earth, older than oceans, older than life itself. Asteroid Bennu, carbon dark, fragile, and seemingly inert, has circled the Sun for billions of years, carrying within it untouched records of cosmic history. When NASA's spacecraft reached out and touched its surface, it was not searching for something alive, nor something dangerous. It was searching for origins. Yet what came back was neither simple dust nor ordinary rock. It was something stranger, something that did not fit comfortably into expectation. This substance did not glow or pulse. It did not announce itself dramatically. But in laboratories on Earth, it quietly unsettled scientists who had spent decades believing they understood primitive asteroids. Its chemistry hinted at reactions that should not have happened so easily. Its structure suggested processes that blurred the boundary between geology and prebiotic chemistry. Bennu, once thought to be a passive relic, suddenly felt active, almost purposeful, in the way it preserved and delivered this material across deep time. If asteroids are time capsules, then Bennu's contents were not merely records, they were messages. Messages written before planets fully formed, before Earth cooled, before biology learned how to begin. And as researchers examined these grains under microscopes and spectrometers, a deeper question emerged. Was this substance simply ancient matter, or was it evidence that the building blocks of life were far more widespread, far more prepared, than humanity ever imagined? In the quiet of clean rooms and cosmic simulations, Bennu began to whisper an unsettling idea, that life's ingredients may not be rare accidents, but inevitable consequences of the universe itself. The story does not begin with a rock drifting through space, but with a question forming quietly inside laboratories and conference halls on Earth. For decades, planetary scientists had searched for a way to hold the early solar system in their hands, to examine matter untouched by planets, weather, or life. Telescopes could observe, spectrometers could infer, but certainty required something more intimate. It required a return. In September 2016, that intention took physical form as NASA's OSIRIS-REx spacecraft rose from Cape Canaveral and vanished into the black above Earth's atmosphere. Its destination was a near-Earth asteroid named Bennu, a small, dark body orbiting the Sun on a path that occasionally crosses Earth's own. Bennu was not chosen for spectacle or danger, but for restraint. It was carbon-rich, primitive, and believed to be a surviving fragment from the solar system's first few million years. In theory, Bennu had remained chemically simple, preserved like ash beneath stone, unchanged since planets were still assembling themselves from dust. OSIRIS-REx was designed with surgical precision. Its instruments were not built to dramatize space, but to listen to it. Cameras would map Bennu's surface in detail. Spectrometers would read the chemistry of its skin. A robotic arm would briefly touch the asteroid, collect material, and retreat. The mission promised answers not through inference, but through direct evidence. Matter carried across billions of years and delivered intact to Earth. When OSIRIS-REx arrived at Bennu in December 2018, the first surprise emerged immediately. Bennu was not smooth. It was not gently dusted with fine regolith as models had predicted. Instead, it was jagged and hostile, a chaotic landscape of boulders stacked upon boulders, as though gravity itself had struggled to organize it. This roughness was more than an inconvenience. It hinted at a violent history of fragmentation and reassembly, suggesting Bennu was not a simple monolith but a rubble pile, debris held together loosely by gravity and time. As the spacecraft settled into orbit, its instruments began reading Bennu's surface in wavelengths invisible to the human eye. The data revealed absorption features associated with hydrated minerals, clays altered by the presence of water. This was not water frozen in place, but evidence of chemical reactions that required liquid water in the asteroid's distant past. The implication was subtle but profound. Bennu itself was too small to sustain internal heat today, yet its parent body must once have been large enough, warm enough, and chemically active enough for water to circulate through rock. Asteroids were not meant to remember water. In classical models, they were cold leftovers, dry, inert, and static. Yet Bennu carried chemical scars of a time when liquid water reshaped its minerals from within. This discovery reframed the asteroid from a passive remnant into a witness of ancient processes, preserved not in motion, but in mineral structure. Over the next 2 years, OSIRIS-REx mapped Bennu in extraordinary detail, searching for a site safe enough to attempt sample collection. The task grew increasingly complex as the spacecraft's data contradicted expectations. The asteroid's surface offered few regions free of hazards. Every potential sampling site had to be studied not only for safety, but for scientific value. The goal was not merely to collect material, but to collect the most pristine material possible, grains that had spent minimal time exposed to solar radiation or micrometeorite impacts. In October 2020, after years of observation and planning, OSIRIS-REx descended slowly toward Bennu's surface. The maneuver, called touch and go, was designed to last only seconds. The spacecraft extended its sampling head, contacted the surface, released a burst of nitrogen gas, and captured dislodged material before retreating. For a brief moment, human engineering and ancient cosmic matter met across millions of kilometers of emptiness. When images confirmed that the sampling head had collected far more material than expected, so much that particles were visibly escaping, the mission crossed from precision into excess. Bennu, it seemed, had been generous. The sample was sealed, stored, and set on a trajectory back toward Earth. 3 years later, in September 2023, a small capsule streaked through Earth's atmosphere and landed in the Utah desert. Inside was material that had not touched Earth since before Earth existed. Scientists approached it with ritual care, transferring it into ultra-clean laboratories designed to exclude even a breath of terrestrial contamination. Expectations were cautious. Carbon dust, silicate grains, simple organic molecules already familiar from meteorites. The first analyses did not overturn physics. They unsettled assumptions instead. Within Bennu's grains were complex carbon-bearing compounds, including a diverse array of organic molecules richer than those typically found in carbonaceous meteorites. Isotopic ratios suggested formation environments consistent with ancient water rock interactions. Mineral assemblages pointed to chemical alteration under conditions that were neither extreme nor brief, but sustained. These were not exotic substances in the sense of violating known chemistry. They were unsettling precisely because they did not. The chemistry was familiar, too familiar, suggesting that the processes leading toward biological complexity may arise naturally wherever carbon, water, and time coincide. As weeks turned into months, instruments confirmed that Bennu's material was chemically reactive, structurally delicate, and astonishingly well preserved. Some compounds showed minimal exposure to solar radiation, implying they had been shielded beneath the surface for eons. Others bore signatures of multiple reaction pathways, layered histories encoded at the microscopic scale. The discovery did not arrive as a single announcement or dramatic press release. It unfolded slowly through peer-reviewed papers, cautious statements, and collaborative analysis across institutions. Each new result added weight rather than spectacle. Bennu was not rewriting chemistry, but expanding its stage. What scientists had expected to be a simple archive of primordial dust revealed itself as a record of chemical evolution, one that occurred long before Earth's oceans formed, long before biology emerged to claim complexity as its own. Bennu was no longer just a target of opportunity. It became evidence that the early solar system was chemically alive, experimenting quietly across countless small worlds. In that realization, the discovery phase reached its true conclusion. Not with certainty, but with destabilization. The assumption that complexity requires planets, atmospheres, or life itself had begun to erode. Bennu had delivered something subtler than an answer. It had delivered a challenge, etched not in theory, but in matter carried patiently through cosmic time. The shock did not arrive as a headline or a single anomalous reading. It emerged slowly, through repetition, through consistency, through patterns that refused to disappear under scrutiny. In the clean rooms where Bennu's grains were first examined, scientists did not encounter one unexpected molecule. They encountered a network of chemistry, interlocking, resilient, and deeply suggestive. Within the dark dust were organic compounds that echoed structures long associated with biology's foundations. Carbon chains arranged in familiar configurations. Nitrogen-bearing molecules resembling precursors to amino acids and nucleobases, the chemical letters that later spell proteins and genetic code. None of these compounds were, by themselves, evidence of life. That distinction mattered. Yet their coexistence, diversity, and distribution told a more unsettling story. What disturbed researchers was not novelty, but survival. These molecules had endured. For billions of years, Bennu and its parent body had been exposed to radiation from the sun, to cosmic rays from distant supernovae, to collisions that shattered larger asteroids into rubble. Such forces are known to break chemical bonds, to erase complexity, to reduce molecules to simpler forms. Yet here, within grains no larger than sand, complexity had persisted. Asteroids like Bennu were expected to be chemically primitive in the narrowest sense. Unprocessed leftovers from planet formation, inert records of the solar nebula. Their role in scientific models was archival, not creative. They were meant to preserve, not participate. But the data emerging from Bennu's samples quietly dismantled this assumption. Isotopic analysis revealed that many of Bennu's minerals had undergone aqueous alteration. Hydrogen and oxygen ratios pointed to interactions with liquid water early in the asteroid's history. Clays and carbonates, minerals that do not form in dry environments, were present in measurable abundance. Their crystal structures recorded chemical reactions that required time, heat, and fluid circulation. This was not a brief contamination event. It was a sustained internal process. The implication was stark. Bennu's parent body must once have been large enough to retain heat, likely generated by the decay of short-lived radioactive isotopes such as aluminum-26 in the early solar system. That heat would have melted internal ice, allowing liquid water to percolate through rock. In those narrow pores and fractures, chemistry unfolded slowly, driven not by biology, but by physics and thermodynamics alone. This scenario contradicted a long-standing boundary in planetary science. Complex chemistry, it was thought, belonged to planets, worlds with atmospheres, stable temperatures, and long-term geological cycles. Small bodies were too cold, too transient, too fragmented. Bennu's minerals suggested otherwise. They recorded a period when size mattered less than timing, when even modest bodies could host chemically rich environments if they formed early enough. The presence of hydrated clays was especially unsettling. On Earth, such minerals are catalysts. Their layered structures can trap organic molecules, concentrate them, and promote reactions that build complexity. Laboratory experiments have shown that clays can assist in forming longer carbon chains and even support primitive self-assembly processes. No life is required, only chemistry given patience. In Bennu's samples, clays and organic compounds were not merely coexisting. They were entangled. Organic molecules were found adsorbed onto mineral surfaces, shielded from radiation, preserved within microscopic niches. This suggested a partnership between rock and carbon that extended over geological timescales. The asteroid, once imagined as sterile, now resembled a quiet chemical workshop, one that operated without intention, without memory, yet with remarkable efficiency. Carbonates added another layer of unease. These minerals form when carbon dioxide interacts with liquid water and rock. Their presence implied that carbon was not merely present, but mobile, cycling through different chemical states. This hinted at a system where carbon chemistry was dynamic rather than frozen, capable of exploring multiple molecular pathways before being locked in place by cooling and fragmentation. Together, these findings eroded the clarity of a once simple classification. Bennu could no longer be described as merely lifeless matter, nor could it be called a biological environment. It existed in a liminal state, between geology and biology, between archive and experiment. The shock deepened as researchers compared Bennu's chemistry with that of carbonaceous meteorites that have fallen to Earth. Meteorites often show signs of heating during atmospheric entry and terrestrial contamination. Bennu's samples, by contrast, were pristine. Their chemistry had not been filtered by Earth's environment. What scientists were seeing was not altered by oceans, oxygen, or life. It was solar system chemistry in its native state. That distinction mattered, because if such complexity exists independent of planets, then Earth's early chemistry may not have been unique. It may have been supplemented, perhaps even initiated, by material delivered from space that was already chemically prepared. This realization did not resurrect outdated notions of life arriving fully formed from the stars. It suggested something subtler, that the universe may routinely produce the ingredients of life wherever conditions briefly allow. That planets may inherit chemistry rather than invent it. The shock was not that Bennu contained organic molecules. Such discoveries had been made before. The shock was coherence. The molecules formed a system, supported by minerals, preserved by structure, and stabilized by time. This was not chemical noise. It was chemical memory. As models were updated, long-held assumptions began to loosen. The boundary between small bodies and planets blurred. The requirement for atmospheres weakened. The notion that life's building blocks require rare environments felt increasingly fragile. If Bennu's parent body, long destroyed, long forgotten, could host water-driven chemistry for even a few million years, then the early solar system may have been filled with similar laboratories. Thousands of small worlds, briefly warm, briefly wet, each running its own chemical experiments before freezing into silence. This perspective unsettled more than models. It unsettled narratives. Life had long been framed as an improbable accident, a narrow outcome of delicate conditions. Bennu suggested an alternative framing. Not that life is common, but that chemistry leans toward complexity. That given carbon, water, and time, the universe repeatedly explores the same pathways. The asteroid did not claim that life must arise. It implied that the steps toward life are not guarded by impossibility, but by contingency. That biology may be less an exception and more a continuation. In that sense, the scientific shock was philosophical as much as empirical. Bennu forced a reconsideration of origins not as a singular miracle, but as a distributed process, one that began long before Earth formed oceans or skies. The samples did not answer how life begins. They revealed how little resistance the universe offers to the attempt. Once the initial shock settled, curiosity took its place. Bennu's grains were no longer curiosities to be catalogued, but evidence to be interrogated with the full precision of modern science. The investigation moved inward, away from headlines and toward instruments capable of listening to matter at the atomic scale. In laboratories designed to exclude even the faintest trace of Earth, scientists began the slow work of translation, turning dust into history. Mass spectrometry became one of the first languages used to question Bennu's material. By ionizing individual molecules and measuring their masses with extreme accuracy, researchers could identify the molecular fingerprints hidden inside the grains. What emerged was not randomness, but structure. Carbon-based molecules appeared in families, sharing backbones and functional groups that suggested common formation pathways. Some were simple, others unexpectedly intricate, hinting at chemistry that had unfolded step by step rather than in isolation. Isotope analysis added another dimension. Hydrogen atoms, nearly identical in form, carry subtle differences depending on their origin. By measuring ratios of hydrogen isotopes, protium and deuterium, scientists could trace the history of water within Bennu's parent body. The results pointed away from Earth-like contamination and toward ancient reservoirs of water that existed in the early solar system. This water was not fleeting frost. It had flowed, reacted, and altered rock from the inside. Carbon isotopes told a complementary story. On Earth, biological processes favor lighter carbon isotopes, leaving distinct signatures. Bennu's carbon ratios did not match biological patterns. They aligned instead with non-biological, abiotic chemistry, confirmation that complexity here arose without life's intervention. The molecules were not relics of organisms, but products of physics and chemistry operating patiently in darkness. To understand how such chemistry could persist, scientists turned to synchrotron radiation facilities, vast machines that generate intense beams of X-rays capable of probing matter at microscopic resolution. These beams revealed the internal architecture of Bennu's minerals, mapping atomic arrangements and defects frozen into crystal lattices. Within those structures were records of temperature and pressure, encoded not as numbers, but as distortions in geometry. The mineral lattices spoke of warmth, not the heat of planets or magma, but a gentle internal warming sustained over time. Temperatures high enough to melt ice, low enough to preserve delicate molecules. This balance mattered. It suggested a narrow window in which chemistry could evolve without being erased. Taken together, the data began to outline a parent body very different from the inert asteroids seen today. Early in the solar system's history, Bennu's ancestor was likely a larger object, rich in ice and dust, forming within a few million years of the Sun's birth. Radioactive isotopes embedded within its rock released heat as they decayed, warming the interior from within. Ice melted. Water flowed through pores and fractures. In those confined spaces, minerals met liquid water and dissolved ions. Chemical gradients formed. Reactions followed. Carbon-bearing compounds interacted with rock surfaces, bonded, detached, recombined. This was not biology, but it was not chaos either. It was chemistry unfolding under constraints, exploring a limited but fertile landscape of possibilities. Microscopic examination revealed layered chemical histories. Some grains showed multiple generations of alteration, earlier minerals overprinted by later reactions. This layering implied time. Not a single episode of heating, but sustained activity, possibly lasting hundreds of thousands to millions of years. Bennu's chemistry was not an accident. It was a process. What made this realization unsettling was its generality. The conditions inferred for Bennu's parent body were not extreme or rare. They were the natural consequence of early solar system physics. Any sufficiently large, ice-rich body forming early enough could have experienced similar internal warming. This suggested that Bennu was not an exception, but a representative. The investigation also revealed how Bennu preserved its chemistry. Organic molecules were often found bound to mineral surfaces or trapped within fine-grained clays. These associations acted as shields, protecting fragile compounds from radiation and mechanical stress. The minerals did not merely host chemistry, they curated it. They selected which molecules survived, which were stabilized, which endured long enough to be delivered across space. This partnership between rock and carbon reshaped how scientists viewed asteroids. They were no longer passive couriers delivering random molecules to planets. They were environments, temporary, limited, but active, where chemistry could mature before being dispersed. As the analysis deepened, comparisons were made with samples from other missions, including Japan's Hayabusa 2 return from asteroid Ryugu. Similar patterns emerged: hydrated minerals, organic compounds, evidence of water-driven chemistry. Each comparison strengthened the case that these processes were not isolated. They were systemic. The phrase, prebiotic chemistry, gained new weight. It no longer referred only to early Earth, with its oceans and lightning and volcanic gases. It extended outward, into the rubble of small worlds, into environments without skies or seasons. Chemistry, it seemed, did not require grandeur. It required opportunity. This realization complicated the narrative of origins. If life's building blocks formed readily in small bodies, then Earth's early chemistry may have been supplemented, perhaps even accelerated, by material arriving already prepared. The planet did not start from nothing. It inherited a legacy of reactions begun elsewhere. Yet the investigation resisted easy conclusions. No single molecule crossed the threshold into life. No structure resembled a cell. Bennu's chemistry stopped short of biology. That boundary remained intact. But the distance between the two appeared shorter than once believed. Each analytical technique, mass spectrometry, isotope tracing, synchrotron imaging, added clarity while deepening uncertainty. The more precisely Bennu was understood, the broader its implications became. The asteroid was no longer a single object, but a window into a common phase of planetary system evolution. The deeper investigation transformed Bennu from evidence into context. It showed that prebiotic chemistry does not announce itself dramatically. It accumulates quietly, layer by layer, reaction by reaction, until it is frozen by circumstance or carried onward by chance. In that sense, Bennu's greatest contribution was not a molecule, but a narrative written in mineral and isotope. A narrative suggesting that wherever water and carbon briefly meet, chemistry begins to lean forward, testing complexity, assembling fragments, leaving behind traces that endure long after the environment itself has vanished. As the investigation widened, Bennu ceased to be a singular anomaly and began to feel like a threshold. The deeper scientists examined its chemistry, the more it resisted containment within existing categories. It no longer fit comfortably as a primitive leftover, nor could it be framed as a mere delivery vehicle of random molecules. Bennu pointed towards something more unsettling, a universe in which chemical complexity is not delicate, not fleeting, and not easily extinguished. For decades, the prevailing narrative held that life's chemistry was fragile, that complex organic molecules required narrow conditions and careful protection, that outside the stable environments of planets, chemistry tended toward simplicity. Bennu undermined that assumption quietly, through evidence rather than argument. Its compounds had not only formed, they had endured. Asteroids like Bennu exist in environments saturated with destructive forces. Solar radiation strips electrons. Cosmic rays penetrate matter at near-light speeds. Collisions shatter rock and expose fresh surfaces to vacuum. Over billions of years, such processes were expected to erase complexity, not preserve it. Yet Bennu's organic compounds survived, embedded in minerals, shielded by structure, stabilized by association. Complexity, it seemed, was not as vulnerable as once believed. This resilience forced a re-evaluation of origins. If small bodies could host and preserve prebiotic chemistry, then Earth's early molecular inventory may not have been assembled entirely in place. The planet may have been a recipient rather than an inventor, its surface seeded repeatedly by impacts delivering material already shaped by chemistry elsewhere. Geological evidence supports this possibility. During Earth's first few 100 million years, the inner solar system experienced intense bombardment. Asteroids and comets collided with forming planets, delivering water, carbon, and volatile compounds. Bennu-like bodies, rich in hydrated minerals and organics, would have been frequent visitors. Each impact was not merely destructive. It was additive. This reframed asteroids as agents of distribution, not carriers of life itself, but couriers of preparation. They moved chemistry across space, spreading molecular diversity from one environment to another. In this view, planetary surfaces became meeting grounds, places where imported chemistry mixed, reacted, and continued evolving. The idea was not new. Hypotheses such as lithopanspermia and molecular panspermia had circulated for decades, often at the edges of mainstream acceptance. What Bennu contributed was grounding. Its samples provided tangible evidence that complex, life-adjacent chemistry can arise independently of planets and survive long enough to be delivered intact. Even more unsettling was the implication of scale. Bennu is not unique in composition or origin. Carbon-rich asteroids are common. Many formed early, when radioactive heating was strongest. Many likely hosted similar episodes of internal water circulation. If Bennu preserved such chemistry, then countless other bodies likely did as well. The solar system, once imagined as a sparse collection of inert debris punctuated by a few active worlds, began to resemble a distributed chemical network. Small worlds, briefly warm and wet, conducted experiments in complexity before freezing or fragmenting. Their products were scattered by collisions and gravity, woven into the fabric of planets still assembling. The mystery deepened further when resilience was considered not just in space, but in time. Bennu's chemistry endured not thousands or millions of years, but billions. This challenged assumptions about molecular lifetimes. Complex organics were thought to degrade quickly under radiation. Yet when bound to minerals, shielded in micropores, or buried beneath surfaces, they could persist far longer than expected. Laboratory experiments support this mechanism. Studies show that clays and carbonates can protect organic molecules from ultraviolet radiation and cosmic rays, acting as molecular vaults. Bennu's samples bore the marks of such protection. Minerals were not passive backgrounds, they were active participants in preservation. This raised a disquieting thought. If chemistry, once initiated, is difficult to erase, then the universe may accumulate complexity over time rather than lose it. Each generation of stars enriches space with heavier elements. Each protoplanetary disk assembles carbon, oxygen, nitrogen. Each small body becomes a potential incubator. Chemistry does not reset. It layers. From this perspective, life's building blocks may not be rare accidents, but common consequences. Not guaranteed, but favored. The universe does not require intention to move toward complexity. It requires repetition. The mystery expanded outward, beyond Bennu, beyond the solar system. Observations of protoplanetary disks by telescopes such as ALMA and the James Webb Space Telescope have revealed organic molecules forming around young stars, methanol, formaldehyde, complex hydrocarbons. These molecules appear early, before planets fully form. They exist in environments colder and harsher than Bennu ever experienced. If such chemistry is present at the birth of planetary systems, then asteroids may simply be one phase in a larger continuum. Interstellar clouds form molecules. Disks concentrate them. Small bodies process them. Planets inherit them. Biology, if it emerges, continues the sequence. In this continuum, Bennu occupies a critical position. It represents chemistry paused mid-trajectory. Not primitive enough to be inert. Not advanced enough to be alive. It is a snapshot of potential. This realization deepened the philosophical unease. Humanity had long framed itself as an improbable outcome, balanced precariously on a narrow ridge of conditions. Bennu suggested that the ridge may be wider than assumed, that the steps leading toward life are explored repeatedly across space and time, even if life itself remains rare. The escalation was not toward certainty, but toward humility. Each conclusion opened further questions. If chemistry is common, why is biology not visibly everywhere? What barriers remain between molecules and cells? Are those barriers universal, or contingent on planetary history? Bennu did not answer these questions. It sharpened them. It demonstrated that the early stages of complexity do not require Earth-like conditions. They require only carbon, water, energy, and time. And those ingredients are abundant. The mystery also reframed extinction. If chemistry is resilient, then catastrophic events may not erase progress entirely. They may redistribute it. A shattered asteroid does not lose its chemistry, it spreads it. A collision does not end reactions, it relocates them. In this sense, the universe appears less fragile than imagined. More patient, more iterative. It tests pathways repeatedly, across scales and epochs, without memory but with persistence. As Bennu drifted silently through space for billions of years, its chemistry waited. Not for discovery, but for context. Only now, in laboratories on Earth, did its implications begin to unfold. The escalation was not dramatic. It was cumulative. A realization built not on spectacle, but on consistency. Bennu challenged the idea that life's chemistry is rare. It challenged the idea that planets are its sole birthplace. And in doing so, it transformed a single asteroid into a symbol of a broader cosmic tendency. The mystery no longer belonged to Bennu alone. It belonged to the universe, and to the quiet question of how far chemistry can go when nothing stops it. As evidence accumulated, certainty retreated. Bennu's chemistry was real, measurable, repeatable, but its meaning remained unresolved. To understand how such complexity could arise, persist, and arrive intact across billions of years, scientists turn not to a single explanation, but to a constellation of theories. Each offered a fragment of coherence. None offered closure. The most grounded framework begins with water. Aqueous alteration remains the central pillar of interpretation, supported by mineralogy, isotopes, and laboratory replication. In this view, Bennu's parent body formed early, while short-lived radioactive isotopes such as aluminum-26 were still abundant. Their decay released heat from within, melting internal ice and sustaining liquid water for extended periods. This water percolated through porous rock, dissolving ions, mobilizing carbon, and driving chemical reactions that reshaped minerals and molecules alike. In these confined environments, chemistry gained structure. Water acted not merely as a solvent, but as an organizer, aligning reactions, transporting materials, and enabling repeated cycles of bonding and rearrangement. Laboratory simulations have demonstrated that such environments can synthesize a wide range of organic compounds without biological intervention. Bennu's mineral record aligns closely with these models. The theory explains how chemistry could emerge and mature within a small body, yet it leaves an unanswered question. Why did so much of that chemistry survive? To address this, researchers turned outward, beyond the asteroid, toward origins that predate the solar system itself. The theory of cosmic inheritance proposes that many of Bennu's organic molecules did not form within its parent body, but were inherited from interstellar space. Observations of molecular clouds, cold, diffuse regions between stars, have revealed a surprising richness of organic chemistry. Even in temperatures near absolute zero, simple reactions occur on the surfaces of icy dust grains, forming alcohols, aldehydes, and complex hydrocarbons. These interstellar molecules become embedded within collapsing clouds that give birth to new stars and planetary systems. In this view, Bennu's chemistry began long before the Sun ignited. The asteroid did not invent its molecules. It preserved and modified them. Aqueous alteration then acted as a secondary process, reshaping inherited chemistry rather than generating it from nothing. This layered origin, interstellar inheritance followed by asteroid processing, offers a compelling explanation for both complexity and resilience. Molecules formed in space are already adapted to harsh conditions. Embedded within minerals and shielded from radiation, they can persist through planetary formation and beyond. Bennu, then, becomes not a cradle of chemistry, but a curator, selecting, protecting, and subtly refining a molecular legacy older than the Sun. From this perspective, asteroids occupy a transitional role. They bridge cosmic chemistry and planetary chemistry, carrying forward molecular structures across environments and epochs. The theory fits observational data well, yet it still leaves uncertainty. Why do certain molecules appear repeatedly across different environments? Why do some pathways dominate while others fade? Here, speculation moves toward probability rather than environment. Some researchers look to quantum chemistry and statistical mechanics for insight. At the molecular level, not all reactions are equally likely. Certain configurations are energetically favored. Certain pathways are easier to traverse. Over immense timescales, even small statistical biases can shape outcomes. In this framework, Bennu's chemistry reflects universal tendencies. Given carbon, hydrogen, oxygen, and nitrogen, certain molecular forms arise again and again, not by chance, but because physics favors them. Amino acid precursors, nucleobase-like structures, and stable carbon chains may be attractors in chemical space. The universe does not explore chemistry evenly. It leans. This idea is supported indirectly by observations beyond the solar system. Similar organic molecules appear in interstellar clouds, protoplanetary disks, meteorites, and comets. The repetition suggests convergence rather than coincidence. Bennu's chemistry may feel prepared not because it was designed, but because it follows pathways that matter naturally finds. Such speculation edges toward philosophy, yet remains grounded in physics. No intention is required, only energy landscapes, reaction kinetics, and time. Other researchers revisit a long-standing and often misunderstood concept, panspermia. In its modern, restrained form, panspermia does not claim that life itself travels between worlds. Instead, it suggests that life's chemical toolkit, its ingredients and intermediate steps, may be distributed across space. Bennu fits comfortably within this interpretation. It carries no organisms, no cells, no replication. It carries preparation. In this view, Planets are not isolated laboratories. They are nodes in a network, exchanging material through impacts and debris. Chemistry migrates. Each environment modifies it further. Life, if it arises, does so locally, but from ingredients assembled globally. This framework remains speculative, but Bennu lends it credibility by demonstrating that complex chemistry can survive transit and time. The asteroid does not prove panspermia. It removes one of its largest objections. To contextualize all of this, scientists often invoke the language of deep time, a perspective shaped by relativity and cosmology. Einstein's theories remind us that time is not absolute. Billions of years, compressed into microscopic grains, become accessible through measurement and inference. Bennu's chemistry is not ancient in an abstract sense. It is ancient in a measurable one. Its isotopes, structures, and reactions are timestamps written in matter. This compression of time challenges intuition. Processes that seem improbable on human timescales become inevitable given enough duration. A reaction that occurs once in a trillion collisions becomes common if allowed to run for millions of years across countless environments. Bennu's chemistry may not be remarkable because it happened, but because it stopped, frozen when its parent body broke apart and cooled. Modern astrochemistry increasingly adopts this perspective. Rather than asking whether complexity can arise, it asks how often and under what constraints. The question shifts from possibility to frequency. Yet for all these theories, aqueous alteration, cosmic inheritance, statistical chemistry, molecular panspermia, none fully resolve the central unease. Bennu's chemistry appears not only complex, but coherent. It feels aligned, as though multiple processes converged rather than interfered. Why this convergence occurs remains unclear. One possibility is selection without life. Chemical systems that stabilize themselves persist. Those that do not, vanish. Over time, environments like Bennu's parent body may favor molecules that bind to minerals, resist radiation, and survive disruption. What remains is not random chemistry, but filtered chemistry. Robustness emerges without intention. Another possibility is incompleteness in current models. Bennu's samples represent a tiny fraction of a much larger system. Processes that seem improbable in isolation may be common in aggregate. The asteroid may be ordinary, while assumptions have been narrow. What unites all these theories is restraint. None claim certainty. None assert inevitability. They circle the mystery rather than solve it. Bennu's chemistry resists singular explanation because it is the product of multiple layers: interstellar space, early solar system physics, asteroid interiors, and deep time. Each theory illuminates one layer. Together, they suggest that complexity is not born in one place, but assembled across many. In that assembly lies the lingering question. If the universe repeatedly prepares the ingredients of life, why does life itself appear so rare? Are the final steps more constrained? Or is rarity an illusion born of limited observation? Bennu offers no answer. It offers context. It reveals that the universe is not indifferent to complexity. It experiments quietly, persistently, without awareness. Each theory brings scientists closer to understanding how chemistry becomes prepared, but none explain why it stops where it does. Bennu's molecules remain poised, capable, stable, incomplete. In that incompleteness lies the enduring mystery. The asteroid does not explain life. It explains readiness. And that distinction keeps the question open, suspended between physics and possibility, waiting for evidence yet to arrive. The study of Bennu did not end with the arrival of its samples. Rather, it marked the beginning of a broader, more ambitious investigation, one that spans continents, laboratories, and instruments, a global effort to understand how chemistry can persist and evolve in the quiet spaces of the cosmos. Scientists approached the problem not merely with observation, but with replication, simulation, and experimentation. Each tool, each mission, became a lens through which the asteroid's silent story could be interrogated. In laboratories around the world, researchers sought to recreate Bennu's environment. Chambers cooled to near-space temperatures, minerals hydrated with carefully measured water, and radiation applied in doses equivalent to millions of years of solar exposure. Within these controlled spaces, organic molecules were observed forming, bonding, and breaking apart, repeating patterns reminiscent of those preserved in Bennu's grains. These experiments revealed subtle rules. Mineral surfaces not only hosted reactions, but guided them, influencing which molecular forms survived and which were destroyed. Complexity, it appeared, could be coaxed from simplicity under the right constraints, and small differences in temperature, pressure, or water content could profoundly alter the outcome. Beyond the laboratory, other missions expanded the empirical horizon. Japan's Hayabusa 2 spacecraft returned samples from the asteroid Ryugu, offering points of comparison to Bennu's chemistry. By examining similar carbon-rich, hydrated bodies, scientists could begin to discern whether Bennu was exceptional or representative. Each new sample offered a glimpse into a shared evolutionary pattern, a chemical choreography unfolding across multiple worlds in the early solar system. Future missions, including the planned NASA Artemis-era asteroid sample returns, promise to widen this dataset further, extending the investigation beyond a single asteroid to the solar system at large. At the same time, astronomers turned their gaze outward. Telescopes such as the James Webb Space Telescope observe protoplanetary disks around young stars, detecting chemical fingerprints in the cold, dusty regions where planets are forming. Methanol, formaldehyde, and complex hydrocarbons appear in these disks, mirroring the molecules found in Bennu's samples. By correlating space-based spectral data with laboratory results, scientists can begin to map chemical evolution from interstellar clouds to asteroid interiors, connecting isolated findings into a continuous narrative of molecular persistence. Particle accelerators and radiation chambers provide another dimension. Organic molecules in space are constantly bombarded by cosmic rays and ultraviolet photons, processes that, over billions of years, can break bonds and erase structure. By exposing laboratory analogs to controlled doses of radiation, researchers measure stability thresholds and survival rates. These studies demonstrate why Bennu's chemistry endured, embedding in mineral matrices, shielding within pores, and repeated cycling through aqueous environments all contributed to its persistence. Mathematical models complement experimentation. Simulations of early solar system heating and water distribution trace how parent bodies could maintain liquid water long enough for complex chemistry to unfold. Thermal evolution models, combined with impact and fragmentation histories, indicate which small bodies could have served as effective chemical laboratories and which would have lost their potential through rapid cooling or disruption. Each model adds granularity, narrowing the parameter space that could produce molecules like those found on Bennu. Yet, as with all science, each answer unveils new questions. Experiments replicate some aspects of Bennu's chemistry, but rarely all. Models suggest potential pathways, but cannot predict which molecules should dominate or why certain structures persist. Observations detect familiar compounds elsewhere in the solar system, but the broader frequency and distribution remain unknown. Bennu thus serves simultaneously as a case study, a benchmark, and a tantalizing enigma, a reminder that cosmic chemistry operates over scales of time, space, and subtlety that challenge direct intuition. The ongoing investigation emphasizes collaboration. Astrobiologists, chemists, planetary scientists, and astronomers exchange data, hypotheses, and models in real time, each perspective illuminating a different facet of the mystery. Laboratories replicate asteroid interiors, telescopes track molecular clouds, particle accelerators measure radiation resilience, and space missions provide samples impossible to recreate on Earth. Together, these tools form an interconnected network, each reinforcing and testing the other, weaving empirical evidence into a richer understanding of how chemistry organizes itself across cosmic time. Bennu's grains, inert yet profoundly expressive, act as a bridge between disciplines. They remind scientists that the universe preserves memory in unexpected ways, that chemical histories can span billions of years, and that the smallest samples, analyzed carefully, can challenge assumptions about how matter evolves. Each experiment, each observation, reduces uncertainty, yet simultaneously illuminates the vastness of the unknown. In the quiet laboratories and across the distant telescopes, Bennu continues to speak. Its message is subtle, requiring patience, precision, and imagination to interpret. It tells of resilience, of opportunity, of chemical pathways that unfold in silence and persist in the face of destruction. And it whispers that the universe may be more chemically prepared than ever imagined, offering glimpses not only of what has occurred, but of what may yet be possible elsewhere among the stars. Bennu drifts through the void, silent and patient, its surface etched with the memory of billions of years. Within its fractured grains lies a narrative older than our planet, older than our sun. A narrative written not in words, but in molecules, minerals, and the subtle geometry of atoms. These fragments of carbon, hydrated clays, and complex organics do not speak of life directly, yet they carry a quiet implication, that the universe itself does not resist creation, that the chemistry of life may be a natural consequence of matter, energy, and time. In examining Bennu, humanity confronts a paradox. On one hand, we hold in our hands the tiniest remnants of a world we cannot visit directly, a world that formed before Earth existed. On the other, we confront the immensity of possibility, the subtle suggestion that life is not a miraculous accident, but a potential embedded across the cosmos, waiting for circumstances to converge. This is not certainty. It is a tension between evidence and imagination, between what we know and what we feel might be true. Each molecule preserved within Bennu has endured the onslaught of cosmic radiation, the chaos of collisions, the slow erosion of time. Their survival challenges assumptions about fragility and rarity, revealing resilience in unexpected places. It is a reminder that the universe does not merely host chemistry, it experiments with it, iterates upon it, and occasionally preserves its results in silent repositories scattered across space. Bennu is one such repository, a testament to the patient and persistent work of natural forces shaping matter over eons. Through these observations, the concept of human origin itself begins to shift. We are not solely the product of a single planet's improbable history. Our molecules may have traversed asteroids, comets, and interstellar clouds, participating in a chain of chemical evolution that spans light years. The ingredients of life, the scaffolding of possibility, were prepared long before Earth formed oceans or skies. The story of life begins not with a singular miracle, but within a universe already primed for complexity. There is humility in this realization. Humanity's presence on Earth may be extraordinary, yet it is also part of a broader continuum. We are participants in a process older than recorded history, one that began in the cold dust between stars and continues quietly, invisibly, across space and time. Bennu reminds us that life, chemistry, and possibility are inseparable from the cosmos itself. And in that reminder lies both wonder and unease. Bennu offers no answers about extraterrestrial life. It does not claim to reveal our cosmic neighbors. It does something subtler. It reframes the question itself. Life may not be improbable. Complexity may be inevitable. The universe may lean not toward entropy alone, but toward creation, toward the assembly of molecules capable of becoming more. As scientists hold Bennu's fragments in their instruments, as telescopes seek echoes of its chemistry among distant stars, the asteroid whispers across time. It tells of preparation, patience, and persistence. It tells us that the universe is not indifferent. It tells us that we are not isolated. And in that whispered message lies a profound reflection. Our origins, our chemistry, our very existence are chapters in a story that began long before Earth and will continue long after. Bennu does not answer the question of whether humanity is alone. It offers instead something more enduring, a sense that life's ingredients, its potential, its promise, are woven into the fabric of the cosmos itself. That from the smallest grains of ancient rock, possibility can emerge. That the universe, in its quiet patience, has already begun to prepare the next chapter. We are heirs to that preparation and witnesses to its unfolding, carrying within us a legacy written not in human hands, but in the silent, persistent chemistry of the stars.